Hello.
Morning.
Good morning. How are you doing?
I'm good, and you?
Good.
Sir.
I am. Let's see, it's the same thing. I got two notifications for the same Zoom. I'm like, they better not be separate ones. So I did manage to get videos for the lectures uploaded. So they are now on Moodle, and I sent out links to them as well.
Yes.
So that should be good. And today we get into the science, the
Yes.
actual science. And it's kind of
Yeah.
funny. But, with climate science, I didn't know who I was going to get, in this program.
Yeah.
And I've had, even in my biochemistry class, I've had no flat earthers, but I have had people that are very religious, believe that the earth is 5,000 years old and evolution doesn't exist and things like that. So I kind of like to back up the science. And I think it's important for everybody to be able to defend the science that they're going to be operating on. Because as you
Yeah.
become climate actors, you find out that there's lots of headwinds against us. In the US alone, for example, uh, the Republican National Committee has come out with their platform for 2024, and that's for whoever wins office. If a Republican wins office, and they plan to strip everything about climate change across the government, including all of the subsidies and tax credits for electric vehicles, for
Wow.
solar power, wind power, and then they put a lot of money into increasing the amount of fossil fuels like coal and oil and
Yeah.
extraction. And it's like, oh my gosh,
Wow.
you
I
wonder
did
who
not know.
pays for all that. Yeah. Yeah.
Yeah. Well, yeah.
It's their 2024 project. Look it up, see what it's about. And when you're chatting with your friends about it, I mean, regardless of who you like or who you don't like, I've become a single issue voter because this is going to kill us if we don't deal with it.
Wow. So regardless of the two parties, that's the initiative in 2024. Huh?
Yeah.
Wow.
Yeah. That initiative is for whatever Republican wins, whether it's Trump or somebody else. It looks like
Okay.
Trump's going to win the nomination, but who knows?
Yeah.
Um,
Wow.
I want to get started, but I know we're waiting on several more folks, four more people. Um, I'll wait just a minute, but there's a lot that I want to get through, and folks can watch the video, of course. Um, Although it usually takes me a little while to get it out because right after class, I run off for three classes, and then I get back to my desk, and it takes a while to upload. And anyways, um, if you make it to class, no big deal. Okay, I'm going to go ahead and share my screen. Well, actually, first, since we're getting into the actual science, we don't need distractions. And second. Okay, and okay. So wait just a minute. Have you gotten the textbook yet?
Yes, Prof. I got a PDF.
Okay, great. Wonderful. Caldrian, how about you?
Um, I tried the link, but the link it's I think it sent me to a page that wasn't available. Well, it sent me to the
Okay.
actual page, but the book itself wasn't available. So I've been kind of searching online, kind of whatever.
Let me hold on a second. Change. I prefer you get volume 3 if you can. That's the stock image. And there is a way to get online copies. You might actually, why don't you email with Shepard? Do you all have each other's email addresses?
I know they're all linked under the email thread, I believe.
Yes. So if you maybe email Shepard, he might be able to point you in the direction where he got the PDF.
Or-
That's about all I can say on the topic, although I'd like to say more. So we'll just wait a second. How are you doing today, Shepard?
Yes, Prof, I'm doing well.
Good. I'm glad you could make it.
All right, thank you.
I did send out the links to the previous videos from our previous lectures. That's in that email as well that just went out. And I talked to admin on day of the last class. They're working on getting your IDs. I don't know what this holdup is. We have all your documentation. So I'm going to follow it up again today. I've got the chair of the department and the dean of the school both working on it because you and Glory have yet to get Claflin IDs, but everybody else should be able to log into Moodle. Have you gone into the Moodle site yet, Keldran?
Yes.
Okay. And Desire, have you gone into the Moodle site?
Yes, I have.
Okay, great. Because the videos are posted there. And what I'm going to try and do is I'll put up the PowerPoint lecture for each week. I'll put up the PowerPoint lecture, and then after that will be the video of that lecture. And we'll just kind of go along that way, kind of in order during the week. Probably at some point, the beginning of the week, I might put some of the learning objectives. I'll probably retool that at the top of the page by the end of the week based on what we were able to get through. So along on that line, the learning objectives for this lecture is you should be able to explain why temperature is used for the main metric of climate change, how it's measured, what temperature anomalies are, why they're used, how to calculate them. Those are going to be really important. Being able to describe multiple factors that confirm climate warming, to be able to identify and challenge logical fallacies that are often used in anti-climate change arguments. And the importance of that is to really understand the strengths and weaknesses of the science that we're basing all of climate change on. And then lastly, we'll look at the paleoclimate record. That's the record of the distant past. What was it like 100 million years ago in the time of the dinosaurs and before? And we actually have lots of interesting evidence on that as well. So I strongly suggest everybody now read chapter 2. Should have already read chapter 1. They're fairly easy reads. And if you read something, you got questions about it, always feel free to shoot me an email, ask me some questions. I'm always happy to do those. But first, before we get onto the science, I just wanted to present some data on our group because I found it really interesting. I've had you guys fill out a lot of stuff based on learning styles. I wanted to get information about you, etc. And so it turns out our cohort, this is the first cohort for this program, the online program, I'm really excited about it, are from a range of different countries. Brenda's in Zimbabwe, Gloria's in Nigeria, Shepard's in Nakuru, Kenya, Desire's in Manila, Caldrian is in Edwards, Mississippi, and the US, and Nyamanga's in Nairobi. So we've got a whole range of folks from all across the globe. I think that's a great cohort, especially when we're talking about global climate change. In addition to that, I asked you a lot about your learning styles, and just so you get kind of an idea of a range of the group. Now, I'm still waiting. I think Desire and Shepard, both of you still need to do the learning style surveys, I believe. So check that out when you get a chance. But from the data I have, it looks like the class is, while there's some active learners, most of the class is either balanced between the two or more of a reflective learner. So that's kind of interesting. In terms of the class, a great majority of the class are balanced between sensing learning and intuitive learning, with some leaning towards the sensing modality. In terms of sequential versus global learning, I'd say a vast majority of the class is in the sequential format that likes to have information presented kind of in a logical order, piece by piece, and then you put it together at the end. And the rest of the class seems to be balanced between that and global, which is liking to see the big picture first. So the way I'll probably try and do this class is I'll mention the big picture, but then I'll really go through that sequential format and then arrive at the big picture again. And it looks like a large majority of the class are visual learners, or balanced between visual and verbal. So I'll try and use as many graphs and as many pictures and videos as I can. Hopefully you'll find that the use of Flipgrid will also help with that. And it was interesting for me to see how many people agreed with the assessment of their learning style. And then if you did, and you read that article, remember that article suggested a bunch of different strategies depending on your learning style, strategies for studying and for learning material. And it looked like a good number of people already use those strategies. Some folks have tried some of the strategies and are willing to try the others. And then there's also a group that hasn't tried those strategies before, but are eager to try. And I'm glad to see that willingness. It's really important, I think, for us to grow as scientists and grow as learners on this, especially because we're going to deal with pretty complicated material. It was really interesting to read about your stories and your history. One of the things I noticed is there's a lot of similarities in our group based on interests. Seems like everybody's interested in mitigating problems in your home country. For agriculture and farming mitigation, Glory and Imungo and Shepard kind of fall into that group, the main focus that they mentioned. Brendan and Desire mentioned emergent disease mitigation, which is great. And then two of you already work in resource management, Gloria and Caldrian. And I also noticed that some folks are also big fans of soccer or football, as they call it. And that's Shepard and Imungo. So I think it's important for us to know about each other because we're going to be working together a lot. And so if you can see some of the common interests. So I do suggest, I know you all did your introductory video. I do suggest if you can go back and watch the introduction videos of your classmates so you get to know more about them and such. So now back to climate change. Is the climate changing? That's what we're going to first cover in the chapter 2 of the book. And do we really know? And I take it you all have opinions. We've talked about it before. I think the answer is a resounding yes. And not only is it yes, but the change is significant. And as we learn later in the course, when we look at the paleo climate data, we'll even see that climate has always been changing in significant fashion, perhaps not as fast as it is today, though. So during this chapter and the next, we're going to really learn how this is measured and analyzed. And so I want to go back to our previous lecture when we talked about the definition of climate. So climate really is defined as the statistics of the weather over a period of time. Could be several decades, could be the last few years, or could be, a broad span of time, over a millennia, depending. But it's really those statistics of the weather, what you would expect the average day to be at a particular time of the year in a particular location. So in this lecture and for, a good section of the course, we're really going to focus on temperature. And there's a lot of reasons for this. Main reason is the most direct impact from CO2 that we can see is an increase in temperature. And all of the other variables that a lot of people talk about with climate change, which can be extreme weather, precipitation, changes at sea level, melting of sea ice, those are all kind of a response to a change in temperature. So we're trying to go towards the main driving factor, and that's what we'll study first. Also, we have the best data on temperature. People have been measuring temperature both accurately and consistently and around the globe since the middle of the 19th century. The technology for measuring temperature is centuries old. We've all played with and used thermometers, usually the liquid and glass thermometer. Sometimes it's mercury, sometimes it's another liquid. But that technology is really, really old and reasonably accurate. And people around the world have been using these devices and recording the temperatures they observed in their local regions and writing down the date. So we really do have a comprehensive record. And so that's another reason why we focus on temperature. And it's kind of important to understand that, because a lot of conclusions we're going to be based off, we're going to be leaping off from how the temperature's changing. Any questions so far? Okay, it seems pretty straightforward. What might not be so straightforward is how we're going to talk about temperature. We're not really going to talk about absolute temperature. We're going to be talking about temperature anomalies. A temperature anomaly is the difference between an absolute temperature that you measured a specific place and time versus a reference temperature, usually a multi-decadal period, usually around 3 decades. So this slide that I'm putting up here, this is the definition of a temperature anomaly. If you're taking notes, this might be one of the things that I would write down, is this definition. It'll be on our exams, and it'll be something that you really need to be able to explain. So remember, it's defined as the difference between the temperature and a reference temperature based on a previous multi-decadal period. Usually climate scientists like to do periods of around 3 decades or 30 years. And so, for example, to give you an example of what I mean by a temperature anomaly, Houston's temperature in August 2011 on the 15th was 31.3 degrees Celsius. If you look back in the data for Houston in that location for that thermometer, you can find data going all back for a very, very, very long time, over a century. So if you take a period of that, we're going to take the 1951 to 1980 time period, and then from that time period, we're just going to average all the temperatures before August over those 30 years. And when you do that, you get a value of 28.5 degrees Celsius. And so that's the average temperature in August over that 30-year period. Now, when we're measuring the temperature today, or at least in this example in 2011, it was measured, and this, I use that date because it's a figure that was used in our textbook in, I believe that was the first edition. So what you then do to calculate the anomaly is subtract the reference temperature from the measured temperature. So we got 31.3 degrees Celsius minus 28.5 degrees Celsius, which gives us an anomaly of plus 2.8 degrees Celsius relative to that reference temperature. So if the value is plus, if it's positive, that means the temperature is higher, it's warmer. And if the value is negative, that means it's cooler. Makes pretty much sense. Okay. So anomalies are always tied to a reference period. And it's really important how you choose that reference period, and that reference period is significantly long, because our climate, not due to climate change, there's natural weather variations from year to year. You can have El Niños and La Niñas, which can affect the temperatures you might see in that particular year. And so what you try and do is look over a longer time span. Of course, when you're comparing it to the temperature today, like that you're measuring, and you want to calculate the anomaly, you might be in one of those kind of fluctuating periods like a La Nina or El Nino. Temperature anomaly doesn't tell you that. It just tells you is the temperature you're measuring right now atypical versus your reference period. Okay. If you change your reference period, the anomaly is going to change. So for a lot of your measurements, you always want to be consistent and using that same reference period. And again, a long time. Anybody guess why we use anomalies and we just don't use absolute temperature when talking about climate change?
Because anomalies kind of pinpoint exactly the discrepancies between now and several decades ago, which is a good talking point when speaking of climate change, because you can use the point of, hey, on average, it's 10 degrees higher or 5 degrees higher around this time of year in this location as opposed to in 1970. So it's a good strong point when discussing climate change or trying to prove climate change, rather.
Okay. That's one reason. Why couldn't you use absolute temperature though? Pick two dates, say, oh, the absolute temperature's changed. If you look at our example, we talk about the anomaly as being 2.8 degrees Celsius. We're not talking about, the average temperature is now the absolute temperature in the 30s versus the 28s. There's another really important reason why we use temperature anomalies. And that has a lot to do with how temperature can vary from place to place. So here's a picture of Atlanta, Georgia. Okay. About 100 square miles or square kilometers, I'm sorry. And you can see vegetation. So this is a satellite photo. You can see there's vegetation around here. Here's the city center of Atlanta. And then you can see some of the suburbs branching off, some of the roads going out, etc. Now, if one was to look at a heat map of the same region, and so what I'm going to show you next is a satellite photo. This is an infrared satellite photo doing a heat map. Things that are hot radiate infrared radiation. And so here's a heat map. What do you notice about this when you see it? What jumps out at you? Desire, what do you think? What jumps out at you when you see this heat map of this region? Now, things in red are warmer and things in yellow are cooler, okay?
It looks like the one in red it's water and then the one in yellow it's cooler. So the heat is distributed around the central part of Georgia, whereas the peripheral part of Georgia are cooler, but there are specific places where it's warmer than even though it's within the periphery, but there's certain places where it's warmer.
Okay. Notice our distance scale here. This little bar is about 5 kilometers. So this little bar can kind of fit over this whole region right here. So that's about 5 kilometers. I'm gonna go back to the original picture. So we're looking at about 5 kilometers over here. And as you rightly point out, in the region where it's more populated, it's warmer. And there are some places that are really hot compared to something that's less than a kilometer away, which is significantly cooler. You've got this red spot right over here, and then a fairly whitish spot right over here, which is, you know, could be about 12 degrees cooler over here, according to this heat map. And this detail is something that's fairly well-known phenomenon called urban heat islands. Vegetation tends to not get as hot as, say, concrete and buildings. We have lots of concrete and buildings that tends to really absorb a lot of the heat and re-radiate it. So regions in the center of a city where there are buildings and lots of concrete tend to be a lot warmer than places where there are vegetation and trees and water. And so what we end up seeing is this effect where you can get very sharp differences in temperature that are really close together. So temperature can vary greatly over short distances. Now I can keep like trying to do this so you can kind of get an idea, or I'm going to try and merge those pictures a little bit so it's more reddish where it's hot, and you can see that corresponds to, you know, where you've got more concrete and more development. But the point being is temperature can vary a lot over a really tiny distance. So if you've got your thermometer here versus your thermometer just a mile away, you can get really big differences in your readings, significant differences in readings. And, you know, our temperature scale on the satellite map is from 18 degrees Celsius to 30 degrees Celsius. So that's a difference in 12 degrees Celsius. That's way larger than this temperature anomaly, right? So that temperature anomaly, that change would be lost in just taking measurements from one place to another. And so what temperature anomalies do is allow us to kind of correct for that. So we know urban areas are hotter and temperature can change significantly over just tens of meters, okay, just across the street or across the field. And so that means to measure absolute temperature, you would need a ton of different thermometers. Think about it. You'd need thermometers in all of these different places because the temperature is so different. If you really wanted to understand, you know, if the temperature is changing, you know, you can't compare the thermometer here to the one, you know, that's a mile away, or even maybe, you know, half a kilometer away or 30 meters away. So it would take millions of thermometers just to measure this region, and trying to do the whole globe would be almost impossible. And what we find is that anomalies are much more reliable. They're constant over much larger distances. If it's 1 degree warmer in one location, then it will likely be 1 degree warmer 100 kilometers away, even if the absolute temperatures vary greatly. You know, 18 or 30 versus 18 might be 31 versus 19, still a 1 degree warmer temperature difference. And so I'll show you how we go about calculating this, and we'll see if this ends up being true. So we'll look at 2 different cities that are selected by long distance. They're hundreds of kilometers apart. We're going to look at Houston and Dallas. These are 2 examples that are looked at in our textbook. And so I'm trying to use some of the graphs from our textbook. So if you end up reading along and need extra explanation, this will kind of complement that. So our first thing is we need to select a reference period. Okay, so this is our temperature data going all the way from 2020 all the way back to the 1850s. And you can see that on average, Houston is warmer than Dallas, and they're separated by, several hundred kilometers. So different regions experience different outcomes. This is probably more due to there being slightly warmer winters in Houston versus Dallas. But our first goal is to select a reference period. Let's see. And so why don't we start with one location? Let's go ahead and just look at the Houston data. So here's our temperature record for Houston. It's the same one of these two. I'm just expanding this one out. Okay. Now we have to select our reference period. Remember, an anomaly is defined as the temperature of the month that we're looking at to the reference period average. So we have to select our reference period. So we're going to pick between 1951 and 1980. So a 30-year reference period, that's kind of shown right over here. That's the reference period that we're picking. And then to calculate our anomaly, remember it's relative to this reference period average. So we need to calculate the average temperature for Houston over that period, over that reference period. And when you do the calculations for this, you're going to kind of end up somewhere around 20. If you actually do the mathematical calculation, it ends up being 20.7 degrees Celsius. And so we're going to subtract this number from each month to get the anomaly time series. Okay, so we're going to go through each month, subtract that, and get an anomaly time series. And this is what we get. We can go all the way back to the beginning of our data and see, well, once we compare it to the 1950s, what does it look like? Okay, and you can see, so if it's 0, that means there's no difference. And so what we would expect is between 1950 and 1980, by definition, it should be close to 0, but remember, we're doing it at each month. So some months get a little bit warmer and colder. But then we can see how that anomaly changes as we look further back into history and further up into the future. So notice the scale on our left has changed from being absolute temperature here to now to our anomaly temperature. So our largest anomaly is about 1.5 degrees Celsius. So now we have to do the same thing for the second location. Okay, so now we're looking at Dallas. Here's the time series for Dallas. We have to use the same reference period, so 1951 to 1980. We're going to calculate the average for that time period. And you can see it's probably going to be, somewhere around this region of the map, the average. And when you run the numbers on that, you get 18.6 is that average for that reference period, and you're going to subtract that number from each month of your entire time series to get the Dallas anomaly time series. And so that's what this looks like over here. Okay, going all the way back and going all the way forward from that reference period. Again, you're seeing biggest change is probably about 1.5. If you overlay these two and compare these two anomalies, this is what you get. That's significant agreement, right? Even though these cities are hundreds of kilometers apart and experience different climates, average weather temperatures, when you look at the anomalies are almost identical. Look how closely these things track, even though they're separated by a great distance. Again, you can have heat islands or not heat islands, etc. These anomalies allow us to see the signal from climate change, small amounts, differences in a degree and a half, even though the absolute temperatures might be very different. Because if climate change is a real thing and it's causing temperature to increase, that should mean the temperature everywhere is increasing. So it shouldn't matter how many miles apart. If you're a colder area here and you're going to warm by a degree, a warmer area over here should also warm equivalent by a degree as well. So the thing to know about anomalies and why we use them is they tend to be constant over large distances. It's 1 degree warmer one place, it's going to be likely 1 degree warmer 100 kilometers away. And it also means we need fewer thermometers to make these measurements of that region, right? So let's look at the global temperature anomaly, okay? Again, anomaly is calculated by finding an average from a reference period and then subtracting that average. And so this is the global temperature anomaly calculated for 2011. And we're using the same reference period, the average temperatures between 1951 to 1980 in that particular location. So, for example, where you see this little red spot over here, they're subtracting the average temperatures from the reference period from that location to the ones that are being measured in 2011 at that location. Whereas suppose if you go to Australia over here, they're comparing the thermometer readings in 2011 compared to those same thermometer readings back in the 1950s, 60s, and 70s. And so when you calculate these anomalies, remember it's for a reference period at the same location that you took the current readings versus the previous readings, and for your whole time series. Okay, and you'll notice that, well, let me go back before we get to that. So this is just some data on exactly how it's done, how you calculate these. And so if you look at this data, you'll notice that the temperature anomalies aren't evenly distributed. It's not just one smooth temperature anomaly over the entire globe. It seems to be concentrated in certain regions. You'll also notice that these regions are fairly expansive and fairly large, right? We're talking hundreds to 1,000 kilometers across where you see these anomalies change. Some regions are warm, some regions are cool. And throughout the rest of this lecture and future lectures, we're really going to be focusing on the global average temperature because the climate of a particular region can vary significantly just due to weather variability. You know, it might be hot over here in this region of Texas, but then if you go to Northern Europe at the same time, it's a lot colder. And often these are related and reciprocal. And if you average over the globe, you see these regional fluctuations due to weather tend to cancel each other out, and it allows us to see a smaller climate change signal. So often you'll see when it's hotter in one region, it gets cooler in another region. And by using these, averaging the globe, you can really get a stronger signal. And this is what I mean by that. So this is more current data. Again, we're going to use the same reference period from 1951 to 1980. And we're just going to look at, so this one here is looking by the latitudes. This is the 2020 data, looking at the temperature anomaly. And you can see it seems to be getting a lot warmer in the northern hemisphere. And that's partially due to, we know that the temperature on land tends to be warmer than the temperature over the oceans, namely because oceans have water has a high heat capacity, and so it takes more heat to warm water up by a degree Celsius than it does, say, on land. And most of the land on our planet is in the northern hemisphere. So again, we're going to see a lot more of this heat change in the northern hemisphere. So you can see there's a very big difference depending on the latitude that you're at. At really, south of the equator here, changes are a lot less. But as you go north, you can see up to 3.5 degrees Celsius temperature anomaly. That's really significant. So, okay, I want to, go back to this and global temperature anomalies. One of the outcomes of this, because you can see that these cool and hot regions cover large sections, that tells us that we don't need as many thermometers as we would if we were doing absolute temperature, where we need millions for just a small region. Because anomalies can cover larger regions, we could, provided they're well placed, we could actually measure the anomaly of the entire Earth with as few as about 100 thermometers, if they're well placed throughout the globes. And that makes our job a lot easier when it comes to detecting that climate change symbol. So does that answer your question on why and not why use anomalies versus absolute temperatures?
Yes, sir, it does. I think I had the wrong way of thinking when you initially asked, but yeah.
Well, that's the point of this. There's a lot of different ways to think about it, and I think it's really useful to hear what climate scientists have to say that have been studying it and looking at the different perturbations and how they respond to that. I was surprised, at first glance, just how much temperature variability there was from one region to the next that might only be 20 meters away. That was really surprising to me. And then to try and think of the complexity of trying to make global temperature measurements when you have such big temperature differences. But it turns out that these anomalies are kind of the way to go, because those can cover much larger regions. And then if you look at global averages, then you can really see a serious signal on every place is getting warmer by so many degrees, or by large regions. Any questions on how to measure anomalies? Okay, because next week I'm actually going to give you some data sets. You're gonna, I'm trying to find some good data tools that will work in each of your countries, so you can actually look at your regional temperature record, select a reference period, and then calculate what your anomalies are at this current period of time. There's a lot of those tools for working in the US, but I've been trying to look around for what's in Africa and in other regions of the globe that's easy accessible for us to work as kind of a group, because I really want you to kind of wade through the science, if you will, on a hands-on kind of approach. One of the other things I want to point out, any other questions on temperature anomalies? Because what we're going to get into next is the global thermometer network and the temperature surface record. But I do want to draw your attention to our flip for climate change. Hold on a second, shrink this down. If you've seen the introduction page, I've added a new flip. So this is a new peer teaching. This is the first one you guys are going to do. And this is called Justifying Science. So I want you to do this over the weekend. I think I have it set to be due by Wednesday. And so there's about 5 minutes for this video. That's average length. And the question is, imagine that you're completing a biotechnology proposal to mitigate a climate change effect. When you go in to present that proposal to policymakers, one of them says that it's not worth doing. They've read the NIPCC report and they say the climate's actually cooling. More specifically, they can bring you an article in newspaper, in this case, UK News Today, suggesting that the science supporting your particular approach is incorrect. So what I want you to do is tell me how you would address that. Make a 5-minute video countering their claims, justifying your approach, that it's the most likely the best approach, and why their approach, why their data isn't exactly dependable, what they're basing their stuff on. And should be able to do it in about 5 minutes. The link for that, if you go into our week 1 and you scroll down, you'll find that link down at the bottom. It's the last thing for this week, and this will be your first peer teaching video. If you've got your Microsoft account from Claflin, you can continue on with Microsoft and use your Claflin email. But all of you have already done something on Flip already, so you can just sign in the way that you did before. And then I'll give a response to your video. I'll record myself watching it and give you a direct response to it. That'll be sent just to you. And for those that are done very well, I'll post those to the rest of the class so everybody can see. That'll be kind of covering the first material that we talked about in the first 2 lectures about the scientific method and assessment reports, stuff about the NIPCC, etc. It should be pretty easy for you to do. Next week, we'll start doing the flips on calculating anomalies and evidence for climate change. Any thoughts? Comments? So one thing I challenge you all to do is when we're done here, go on the web and type into your Google temperature anomalies and see what you can find. See if you can find information about temperature anomalies in your geographic location. US has a lot of tools. I've been trying to find tools for Kenya, Philippines, etc. But I could use your help. So if you can do a little searching to see if there's a climate tool that allows you to select a reference period and compare it to modern day, or just articles on it, so you can get an idea to what your current temperature anomaly is locally. Okay, thanks everybody. If there's nothing more, I'll say goodbye for the day. I think our time's almost up anyways. So good luck, and I'll see you on Monday.
Thank you so much, Prof. Have a great weekend.
Sure, no
Thank
problem.
you, Prof.
Okay, bye-bye.